Okay, organic compounds, just a few topics we need to cover before we move on to our next big topic on organic reactions. You do not need to copy these diagrams down. This is just a little preview on what we'll be covering. Condensed structural formulas, cyclic hydrocarbons, properties of hydrocarbons, such as boiling point. Okay, so first, condensed structural formulas. Now remember, this is how you have learned how to draw condensed structural formulas. However, at that time, I pointed out to you we could remove the bonds and draw it in a much more compact way. So when you see a structure written like this, you need to be able to name it. Now, you're not going to be asked to draw it like this, but you need to be able to interpret how the information that you're being given, and you need to be able to name it. And so what I will encourage you to do is when you're given a structure like this, a condensed structural formula that has no bonds, rewrite it where you have all the bonds to everything except hydrogen so that you can easily name it. So this, you can see, would be kind of hard to name. Now, to interpret this, simply remember that every carbon needs to have 4 bonds. So this carbon here has 4 bonds, 3 hydrogens and this bond to this carbon. And so that's what's going on here. This carbon is bonded to this carbon and 2 other hydrogens here. Now this carbon has only 1 hydrogen, so we can see that here. And it's bonded to a methyl. And so we have the methyl squeezed in here with parentheses. Sometimes they won't give you parentheses. I will. I'll try to. This carbon, of course, has to have, or can only have 4 bonds. So since it has 3 hydrogens, it has only 1 more bond remaining. So it has to be a branch. Now the CH2s here, we have 3 of them in a row. We could condense this even further, where we have the 3 CH2s written like this. So this is kind of our task, a little puzzle that we need to unpack, is when we're given a structure like this, we need to be able to rewrite it in a form that we can recognize what its name would have to be. Okay, so we're going to do some practice here. Now I encourage you to pause the video and try it yourself once you kind of get the hang of it, but I'm going to just rattle through this. So I'll leave it up to you to pause the video and try it yourself as I go along. Now for this, you have the CH3 and then this carbon. Now this carbon is bonded to 2 methyls. So those will be branches. And then bonded to the remaining chain. So now we can easily name it 2,2-dimethylpentane. Now that was a hydrocarbon, but we also need to be able to interpret when we have functional groups. Now for this, again, all you need to do is remember carbon has to have 4 bonds. And remember the Honk rule. Carbon has 4 bonds, and oxygen, in this case, will always have 2 bonds. So the CH3 bonded to this carbon, and then you have these 2 oxygens. Now you just kind of file away. Anytime you see 2 oxygens, it means that a carbon is going to have a double bond to one of them and a single bond to the other. So that's this. And then this oxygen is going to be bonded to a 2-carbon chain. So hopefully you recognize that this is an ester. Remember that when we name an ester, we bisect the molecule through the single bonded oxygen. We name the side that doesn't have the double bonded oxygen first, and so this would be ethyl. And then we name the side that does have the double bonded oxygen. And this also would be ethyl, but we change the ending to OATE. So the name of this is ethyl ethanoate. Okay, for this will be ethanamide. Remember that if you have a double bonded oxygen and an amine, that's an amide. So ethanamide. So you kind of get the idea here. Just a little puzzle, keeping in mind that the Honk rule again, carbon 4 bonds, hydrogen 1, oxygen 2, and nitrogen 3. So the carbon would have to have a double bonded oxygen at the end to have its 4 bonds, and then the 4 CH2s is just a part of the parent chain. So hexanal. A few more. Now this is an ether. Remember, for an ether, we named the shorter chain first, and so this is 2 carbons long, so it'd be ethoxy. And then the longer chain would be named as if an alkane, so this would be butane. So it'd be ethoxybutane. I feel like I'm going really fast here, but I'm hoping you're pausing the video and trying it yourself first. To pentanone, we would need to have a number to tell us where the double bonded oxygen is. It's a tough one. So this would be our carbon number 1. So 3,3-diaminobutanoic acid. This is the carboxyl group. And 2 amines. Okay, that's it. You'll have some more practice in your homework. You're welcome. Cyclic hydrocarbons, I say cyclic, you can say cyclic. Any hydrocarbon in which the carbon chain joins to itself in a ring-shaped pattern. For these, we use the prefix cyclo. So here's the first 4. Now, when you read a line structure, remember every intersection is a carbon. If there's nothing else drawn to it, then the remaining bonds go to hydrogen. So every endpoint for each one of these that you're looking at, or every intersection, is a carbon bonded to 2 hydrogens because it's also bonded to 2 other carbons. So it's 4 bonds. So 3 carbons is cyclopropane, 4 cyclobutane, 5 cyclopentane, 6 cyclohexane, and they do get bigger. Though you can't have a cyclic hydrocarbon less than 3. Okay, so let's practice this. Again, this kind of falls into place pretty easily once you kind of see what's going on. So we'll name a few of these. Okay, now this is a 4-carbon cyclic chain, so this would be cyclobutane, but we have 2 methyls. Now the methyls could be off the same carbon, or they could be off carbons on opposite sides like this. So we need to have numbers to say where things are. It doesn't matter which one of these carbons we call carbon number 1. It would be a tie either way. So the name of this would be 1,2-dimethyl cyclobutane. Okay, now we have a alkene. We have a double bond here, so that's what's represented by that other line. Now, when we name an alkene that has a branch on it, the convention is, or the rule is that we number through the double bond. So we number through whichever gives us the smallest numbers. So for this, we would number it in clockwise, where this would be our carbon number 1, again, numbering through it. If we were to go in the counterclockwise, well, then this would be carbon number 1, 2, 3, 4, 5, and so our methyl would be on a higher number. So we would number it, in this case, clockwise. So the name of this be 3-methyl cyclopentene. Now we don't need a number for where the double bond is because of this rule that we're following. We number it through the double bond. And so therefore, since the methyl is off of carbon number 3, going backwards, this must be where the double bond begins. If we didn't have the methyl at all, we would just say methyl cyclopentene. We wouldn't need a number because remember, each one of these carbons is exactly the same. Now remember, when we have a methyl and an ethyl, we name the ethyl first because it's alphabetically first. Well, that's kind of a tie here. Which carbon are we going to call carbon number 1? Well, since we named the ethyl first, we'll call this carbon number 1, and the methyl will be off carbon number 2. So I dare you to pause the video, try to name it, but I will now. 1-ethyl, 2-methyl cyclohexane. Now for this, we have halogens on an otherwise hydrocarbon. So this carbon will be our carbon number 1. And so we have 2 fluorines. So this would be 1,1-difluoro 2-methyl cyclopropane. I hope the logic of the IUPAC naming system is kicking in, because once you get it, you kind of impress yourself on your ability to name a compound that you've never seen before. Okay, that's it for cyclic hydrocarbons. Okay, next, and this is a short little topic here, homologous series, compounds that differ from one another by repeating units. Now, this is not exclusive of organic compounds. For organic compounds, though, for hydrocarbons, the unit that is repeating is CH2. Now, you don't need to copy all of this down, but let me make the argument here that that would be true whether it be an alkane, an alkene, or an alkyne. So remember, this is the general formula. So if we start with the smallest molecule possible and move to the next one, well, we simply add one carbon and two hydrogens. One carbon and two hydrogens. And that's the same case whether it's an alkane, an alkene, or an alkyne. Add one carbon and two hydrogens, and we have the next in the series. It's referred to as a homologous series. Carbon classification. Remember, we talked about this with alcohols. Remember, they have primary, secondary, or tertiary alcohols. Well, that kind of goes back to the carbon itself that's bonded to things. So here we're going to look at just the carbons. Now, if it's a primary carbon, we use a 1 degree way to represent it. If it was secondary, 2 degrees, tertiary, 3 degrees, little degree symbol. So this would be primary, secondary, and tertiary. Remember, we're interested in the number of carbons that's bonded to the carbon that we're referring to. So this is a secondary carbon because it has bonded to two other carbons. Okay, so we're going to practice this by looking at 2,4-dimethylhexane. I'm going to draw a line structure for that, and you need to be able to interpret line structures, not draw them, but understand. Now, so we're going to identify which of these carbons are primary, which are secondary, and which are tertiary. So first, primary. Well, primary will be the carbons at the very end, because they're bonded to nothing else but one other carbon. Again, we're forgetting the hydrogens, just the carbons that they're bonded to. For secondary, it would be these two. This carbon is bonded to this carbon and this carbon to this and this. And then we have two tertiary. This carbon is bonded to three other carbons, as is this carbon. So given a compound, name or structure or whatever, you need to be able to identify which carbon is primary, secondary, or tertiary. Properties of hydrocarbons. There's 4 properties we're going to discuss. First, hydrocarbons are relatively unreactive due to their strong nonpolar carbon-carbon bonding. A big exception to that is combustion reactions that we'll talk about next week or during our next notes. All hydrocarbons are nonpolar. Now, it doesn't matter whether it's a straight chain, whether you have double bonds, whether you have branches. They're all very nonpolar molecules. All hydrocarbons are immiscible in water. Immiscible means they don't mix. Miscible would be they do mix. So let's look at an example. Gasoline, which is a nonpolar liquid, and water, which is a very polar molecule. Now, gasoline is a mixture of different hydrocarbons, usually between 5 and 10 carbon length chains. Different gas stations, Chevron, Shell, Texaco, they all have their own mixture of hydrocarbons that they tout as being the better of those out there. But it's all just a mixture of different carbon length chains. Now, the reason that gasoline and water don't mix is there's no attraction between the particles. In this nice little animation of this, so you can see the particles here that are trying to dissolve in the solution, well, they don't, because there's no attractive force between them. And so that's what's going on here between the water and the gasoline. The gasoline molecules have no attraction for the water and vice versa, because gasoline is nonpolar. It would be like trying to pick up wooden toothpicks with a magnet, where the water's the magnet and the gasoline's the wooden toothpicks. There's nothing to grab onto. A nice little takeaway here is that like dissolves like. This is a common adage that you may have heard before, a well-known adage. Polar solvents dissolve polar solvents. So for example, alcohol and water dissolve in one another. They're both polar. Likewise, nonpolar solvents dissolve nonpolar solvents, like oil and gasoline. They're both nonpolar, and they would mix together. But for them, it's not that there's an attractive force between them, but there's just no attractive force between any of the molecules, so there's no reason to keep them apart. Four, all hydrocarbons are volatile, which means easily vaporized, turned into a gas, and have low melting and boiling points. However, as a carbon chain increases in length, it becomes less volatile and will have higher melting and boiling points. So this is a plot of carbon chains going from 1 carbon, 2, 3, etc., and the relative relative boiling points of the alkanes. Now, by boiling points, we simply mean above the temperatures given, the substance will be a gas. So above 0 degrees Celsius, all of these substances would be gases. This is due to an increase in the dispersion forces between molecules. So let's draw a couple of molecules here. Well, there's an attractive force between these molecules, but because hydrocarbons are nonpolar, the only attractive force between the molecules is dispersion forces. Now, the shorter the molecule, the fewer the dispersion forces. But the longer the molecule, the more dispersion forces. So you kind of get the idea here. As the chain increases in length, we have more and more dispersion forces between the molecules, which makes it harder and harder to break the molecules apart when they melt or when they boil. Maybe I should mention that or remind you that if something boils or melts, you're breaking, if it's a covalent compound, like an organic compound, the bonds that are broken are intermolecular forces, the bonds that hold together the molecules. Okay, and last, phases of straight chain alkanes at 25 degrees Celsius. Methane, CH4, all the way to C4H10 would be a gas, but once you hit C5H12, the dispersion forces are sufficient for the compound to be a liquid. And that's the case up until C18H38, when the dispersion forces are enough to make it a solid. So between these two, it's a gas, these two a liquid, these two a solid. And why? Because of the dispersion forces. Okay, that is it. That is the end of notes.